let us go into one by one details into the different processes, that means different requirements, different steps. As I have told you earlier, deoxidation is the first and most important requirement in secondary refining. Now, let us try to understand how deoxidation takes place. Deoxidation, the name implies that oxygen has to be brought down. So, now what is the reaction? This is the basic aim, stands for the deoxidant, the metal, the element which is used as deoxidant, and oxygen is dissolved oxygen in liquid steel. This third bracket, incidentally all of you possibly know, means that this M and this O, that means this deoxidant and the oxygen, these are in liquid still, and the first bracket indicates this constituent will be generated first, and then first bracket indicates it should go to the slag, that means it is a slag constituent. So, the reaction is Mx plus oxygen into Y will get you a deoxidant like MxOY. When we are deoxidizing with aluminum, that means the product is Al2O3. So, X is 2, Y is 3. So, 2 aluminum reacting with 3 atoms of, that means 2 atoms of aluminum reacting with 3 atoms of oxygen, giving rise to Al2O3, the molecule Al2O3. So, as I was telling you, M can be any deoxidizer. It can be manganese, it can be silicon, it can be aluminum, it can be calcium. These are the common deoxidizer which can be used in liquid steel for taking care of oxygen. So, what is the product? What is the deoxidation product? If we are using manganese, it is manganese oxide. If we are using silicon, it is SiO2. If we are using aluminum, I have told you Al2O3. If you are using calcium, it is calcium oxide. Sometimes the two elements also can be used, like manganese silicon. If you do, it can be manganese oxide and SiO2 combination. If you are using aluminum and calcium, it is a combination of alumina and CaO. So, depending upon what is M, that means which deoxidizer we are using for killing the steel, we get the product which is known as deoxidation product. Now, if you look at this reaction, the deoxidation product, if you assume that it is a pure oxide, say alumina, when it is forming, it is not reacting with anything, that means it is pure alumina either in liquid steel, and finally it will go to the slag. So, the activity of this oxide we can take it as 1, and since the element M and the oxygen in liquid steel, these are very low in content. We know from basic thermodynamics that if you assume Henry's law for dilute solution, then this H is the activity which can be taken as equal to wet percent, because it is very low, much less than 1 wet percent. So, the equilibrium constant for this reaction Km dash, what is it? Activity of the oxide divided by the activity of the metal multiplied by the activity of oxygen. Of course, depending on the reaction, that means how many atoms are reacting with how many atoms of oxygen, the X and Y will depend. So, now as I have told you, this AMO can be assumed to be 1, and HM and HO, that means the activities of the particular deoxidant, for example say aluminum, let us take, and the activity of oxygen in liquid steel, since these are very present in very small amount, assuming Henry's law for dilute solution, these are activities of these elements can be taken as equal to their wet percent. So, finally, what this reaction finally goes into, that the wet percent of that metal to the power x into wet percent of oxygen to the power y equal to 1 divided by Km dash. So, if this is taken as Km, this can be taken as the deoxidation constant. So, one important relationship is emerging from this, that wet percent of the deoxidant in liquid steel and the wet percentage of oxygen in liquid steel after the deoxidation reaction, when they are in equilibrium, they are multiplication. That means, wet percentage of the deoxidant in liquid steel and the wet percentage of oxygen in liquid steel equal to a constant. We have to keep in mind, that means, whenever we are increasing the amount of deoxidant in liquid steel, we are decreasing the amount of oxygen in liquid steel. So, that means, for good deoxidation we have to add some larger amount of this M. Now, this Wm and Wo, the multiplication of this is constant, I have told you. Now, if you want to look into what is this constant, what are the values of this constant, that will give an indication how good is the deoxidant. So, let us go into the concept called relative deoxidation ability. Why do we tell that aluminum is a good deoxidant, manganese is not a good oxidant, silicon is a moderate deoxidant, calcium is also a good deoxidant? Why do we tell? What are the quantitative figures? How can we be sure? Yes, let us go into this aspect now. I have told you that wet percent of the metal to the power x into wet percentage of oxygen, this metal M is a deoxidant and oxygen is oxygen present as element, dissolved oxygen in liquid steel. So, x M to the power x and O to the power y is constant. So, and this constant, of course, since there is an equilibrium term, is dependent on the free energy of the reaction, this is dependent on the temperature. So, let us assume the temperature of liquid steel is 1600 centigrade, which is a quite a reasonable assumption. So, at 1600 degree centigrade we can find out the values of K from the oxidation reactions and the K for the different oxidizers. I am giving you some rough estimate of this K for different deoxidizers. For manganese it is 0.2 to 0.3, for silicon it is 2 into 10 to the power minus 5, it is aluminum, it is much lower, you just look at the value. Approximately I am giving the approximate 3 into 10 to the power minus 14, some people call it 2 into 10 to the power minus 14, some people give it the value of 5 into 10 to the power minus 14. Look at calcium 10 to the power minus 12. So, can you make out that manganese the value is high, silicon value is lower than that, aluminum and calcium much lower than these values. So, what does it signify? If you look at what is K, wet percent of M and wet percentage of O, that means if these values Km values are low, that means this multiplication also will be low. That means to get the same level of wet percent oxygen in liquid steel, say we want 5 ppm in liquid steel or 10 ppm in liquid steel, the wet percentage of the deoxidant will be much more for manganese, slightly less in silicon and much less for aluminum and calcium. Please try to remember that this equation, this reaction from the oxidation reaction, we can come out with this understanding that K value, that means the deoxidation constant for the common deoxidizers at a reasonable temperature, say 1600 degree centigrade. If the temperature changes, the values will also change. But let us talk about say any particular temperature, say 1600 degree centigrade. The values are given like this: manganese around 0.25, say, silicon 2 into 10 to the power minus 5, aluminum 3 into 10 to the power minus 14, calcium around 10 to the power minus 12. So, that means using the same amount of deoxidizer, that means if the amount of M is fixed, if the value of Km is low, that means soluble oxygen also will be low. So, from this relation we can tell that soluble oxygen will be very low for calcium and aluminum, will be moderate for silicon, but high for manganese. So, we can tell that calcium and aluminum are very potent deoxidizers, very good deoxidizers. They will bring down the equilibrium oxygen content in liquid steel to very low level. Unlike manganese, you cannot get very low amount of liquid, low amount of dissolved oxygen in liquid steel. It will be very high, maybe more than 100 ppm, maybe 150 ppm. So, manganese deoxidation is not very effective. With silicon, it is better than manganese, maybe you can get 40 ppm. Okay. But for aluminum and calcium, you can get a value of less than 5 ppm. These all can be calculated using this particular relationship at a particular temperature. So, we know that what is the criteria for using deoxidation, which deoxidant is better. It depends on the reaction of deoxidation reaction. As I have told you, this is the deoxidation reaction. M is the deoxidant, oxygen reacting with oxygen, finally giving rise to the MXOY type of oxide. Depending on the deoxidant, the deoxidation product is decided. If it is aluminum, it is Al2O3. If it is silicon, it is SiO2. It is calcium, it is CaO. So, from this equilibrium constants, I have shown that weight percentage of the metal to the power x into weight percentage of oxygen in equilibrium in liquid steel to the power y is a constant, and this constant depends only on the temperature and nothing else. So, at a particular temperature, using this relationship, we can find out what amount of particular deoxidant will give rise to what amount of oxygen after deoxidation at equilibrium. So, we can know that what are the deoxidants and how much do you get after deoxidation, what is the amount of oxygen. Now, I have talked about the deoxidation process, how deoxidation takes place. Now, let us know in reality what are the stages, how does deoxidation take place, what are the steps. We talk about deoxidation, there are different stages, we should know all the stages, then only we should understand what are the implications, how it can be facilitated, how it can be enhanced, how it can be more effective. So, as I have told you, how are we doing deoxidation doing? We are adding the deoxidizer in liquid steel. For example, let us tell we are adding aluminum in liquid steel. How do we add aluminum? We are adding aluminum element, we are adding silicon or ferrosilicon in liquid steel. So, first that has to be added in the form of small particles, small, the smaller it is, better it is, it will be faster going into the solution. So, after we add it, there is dissolution of the deoxidizer in liquid steel. So, first we add, then this gets into solution in the liquid steel. So, this silicon or say aluminum or calcium, when you are adding, it is going into solubility of liquid steel. So, oxygen is there in liquid steel, that particular deoxidizer also goes into liquid steel. So, then the chemical reaction will take place between dissolved oxygen and dissolved aluminum or dissolved silicon or dissolved calcium. The reaction, how the reaction takes place, I have already mentioned to you in earlier slides. So, after adding and dissolution, next stage is chemical reaction between dissolved oxygen and dissolved aluminum. So, finally, what happens? What is the reaction product? If it is aluminum, it is alumina. So, alumina will be nucleated and there is some inclusion growth of these alumina particles, initial growth of these alumina particles. The first there is a nucleation of alumina and there is initial growth of these alumina particles. So, these three steps take place very fast, maybe within 2 or 3 minutes all these stages are over. So, at this stage what is the situation? We have added aluminum, aluminum has got into solution of liquid steel. This aluminum in liquid steel is reacting with aluminum in oxygen producing alumina. So, in the process what is happening? The dissolved oxygen and dissolved aluminum have come down because of the reaction, but the product alumina, they are initially they are in the liquid steel, they have nucleated, they have slightly grown to some extent, but this amount is very high alumina. So, from the cleanliness point of view, we have taken care of dissolved oxygen by using aluminum, dissolved aluminum, but there is alumina still in liquid steel, which is the alumina particles, which is a deoxidation product. This has to be removed. So, removal of alumina from liquid steel is necessary to enhance oxide cleanliness and then thereby reducing total oxygen. What is total oxygen? I have told you total oxygen is a combination of dissolved oxygen and oxygen present as oxide inclusion. So, by deoxidation, by the process of deoxidation, we have taken care of, we have reduced dissolved oxygen, but the deoxidation product, which is alumina, it has aluminum as combined oxygen. So, the total oxygen is still high. So, this alumina now has to be removed from liquid steel to the slag. So, then only we can enhance the inclusion, enhance the cleanliness by removing the inclusion alumina. So, in the process reducing total oxygen. So, how it can be done? This further growth of alumina by agglomeration, now this whatever alumina particles have formed, they will try to agglomerate, they will float up and subsequently they will be absorbed by the basic slag. But this takes time. As I was telling you, addition of aluminum, solubility of that aluminum getting into solution, and then reaction of soluble aluminum and soluble oxygen is very fast. But growth of alumina, they are floating up, their subsequent absorption by basic slag, they are, all these stages are time taking, and these are the rate controlling steps. So, we have to be careful how we have to get or how we have to enhance these stages.